Oh, we're going back.
Yeah.
Trigger.
Did your kids enjoy Halloween?
Yeah, this is my favorite.
What did they dress up as?
One just like a soldier. The other one is Iron Man.
Iron Man?
I'm sure Iron Man's really fun.
I never watched the movie.
You never watch.
They're good.
He never has time. He doesn't do anything but work.
No.
Just work and sleep.
Or sing. I play chess.
Play chess.
Who do you play chess with, your kids?
No, they don't like to play chess.
Really?
Yeah.
Who
I
plays
play
with
online.
you?
I play online. I don't know
Oh,
who I'm
online.
playing with.
I played with my dad a lot growing up.
I tried, like my older son is 10 years old. I'm trying to make him, into chess, but he doesn't like it.
Does he like competing though? Like make it a competition? If you win,
No, he doesn't want to think.
He doesn't like it.
how does that compete with chess?
I tried.
Yes,
I didn't have. I wasn't good.
Oh, it didn't matter who they were on. They just
Oh, they made us play against each other.
yeah.
He has a problem, listening to me. Like, well, sometimes when we play, I tell him, okay, look, the next step, I'm gonna, you're gonna be checkmate. Okay, he's like, shh, just play. Come on, you're not listening.
Are they into sports?
No.
No. What do
Video
they
games.
like to do? Video games.
Oh yeah.
I was never allowed a video
No, I was.
console growing up. I'm terrible at it. I'm the person that hits all the buttons and spins around in circles.
They play on the computer, the iPad, the phones, but I don't have like a console, like an Xbox or something like that. The older one, he's saving. He wants what?
PS4?
Hmm?
PS4?
No.
Switch.
Yeah,
Nintendo
Nintendo Switch. Yeah, he's saving for it, and he's waiting for Thanksgiving to to buy it.
Black Friday?
Black Friday. Yeah.
That's good though. That they
Okay.
save money.
It's $300. He thinks that's gonna be 200 on the Black Friday.
Pay more?
It'd probably be like 250.
I don't know.
He's hoping it'll be 200.
He already have the money. He saved the money. But like I told him, if you get any seed, there is no, even if you have the money, I want to allow you to buy.
Ooh. Dang. Put your foot down.
Yeah, I hid a Nintendo under my table for my dad and would play when he would go to bed. Donkey Kong. That was my favorite game.
What does your wife do?
Right now, she is not doing anything, but like previously, she was a dentist.
Oh.
Okay, but she's not allowed to practice here in the U.S. She has to like study for 2 years to be allowed to practice here.
Is that what she's gonna do?
It's so expensive.
Oh.
Just studying for 2 years, it would cost me around $200,000.
200,000?
Yeah.
Why?
So we don't know how she's gonna do that.
Why can't she just work under a dentist here? Like an
No.
intern?
No, she can't. But to practice in the city in the U.S., she has to have like, a license, she has to study for 2 years, even if she already has a degree.
That is crazy.
For medicine, no, they don't. They just have to take some example, the USMLE, and then they practice afterwards. They just have the residency here. You don't pay anything, they actually get paid with the residency here. But for dentistry, no.
Is she gonna find something else to do then? Like, is she gonna switch?
We're thinking that she can be a teacher.
Make her be an engineer.
No, that's
So was it hard for you to get all your stuff switched when you moved?
for engineering, it's not a problem. Yeah, once you get a degree, like my bachelor degree was from Egypt. My bachelor and my master degree was from Egypt. But once you get a master or PhD from the U.S., you're allowed to work here. That's fine.
So you did your PhD here in the
I did
States?
a master and PhD here too.
Where at?
Buffalo, State University of New York, Buffalo, New York.
New York.
Hmm?
In New York.
That's
A little bit different from here, huh? Yeah. This is the sticks.
Okay, so let's start. So today we're gonna go back to chapter 14. Okay, so the stiffness method for the trusses. Okay, I think this way that we covered those chapters. We started with chapter 15 for the beams, and then we're gonna cover trusses, because trusses, how you're gonna do. What we're going to do for trusses is the same as we did for the beams, except that there will be some changes. Okay, so it's, in my opinion, it's better to start with the beams as we did. Okay, not as the book. The book starts with the trusses first. Okay, so now to solve the truss using the matrix structural analysis, we're going to use the same exact procedure used for beams. What was that procedure? What was the steps?
Notation.
Yeah, so the first thing is we identify the kinematic degrees of freedom.
Build decay, stiffness matrices.
Yeah, so the first step is the kinematic degrees of freedom, and then the next step, as you said, finding or calculating each member stiffness matrix. And then the third step is what? Building the overall stiffness matrix. And then the fourth step is you calculate the unknown displacements. And then the fifth step is you find the reactions, and you need to find the internal forces as well. Those are the steps that we had, and those are the steps that we're going to use for solving a truss. Okay? So the same steps. We're not going to change the steps, but the steps themselves are going to be different. So the difference here, the first step, there is no, okay? In the first step, what are the kinematic degrees of freedom for a truss, okay? We need to understand what are the kinematic degrees of freedom for a truss, okay? And see if they are different from what we had for a beam, okay? And then calculating each member stiffness matrix. How does each member stiffness matrix look like, okay? This might be different. Let's see how it's going to be different. And then building the overall stiffness matrix in step 3 here is the same, okay? It's not different, okay? The same way that we build, how do you build the overall stiffness matrix? You map the elements in the overall stiffness matrix from their equivalent, okay, equivalents in the member stiffness matrices, right? And then calculate the unknown displacements. That's going to be the same. The new thing here is calculating the internal forces in the truss members also. That's going to be something new, okay? So the difference that we're going to have between the two methods comes in step 1 and step 2, this step, okay? This is the differences that we're going to have. So the differences, the first thing is the degrees of freedom. So now, if you have a truss member like this, it has a near end and a far end, as we did for the beams, the near end and the far end. What are the allowed degrees of freedom? For the beam element, we had a vertical displacement and a rotation, right? Those were the degrees of freedom in a beam element, right? Now, when we have a truss member, near end and the far end, what are the degrees of freedom? Can there be a rotation, an angle of rotation theta? Let's try to answer this question. What do you know about the truss member? Some basic information that you know about the truss member. What?
The loads are only applied to points.
Yes, the loads are only applied on the nodes, and the nodes are pinned supports. So what do you get out of those two pieces of information? The moment is here, right? If there is no loads, if this node is a pin, this node is a pin, so the moment here is 0, the moment here is 0, there is no loads, intermediate loads here, so the moment everywhere is 0, okay? So you know that M is 0. The moment is 0. This is a very basic piece of information that we know, okay, for truss members. And you know that d2y by dx squared, this is for any member, whether it's a beam or a frame or any member, d2y by dx squared is m divided by ei. You can have a negative sign in front of it or not, depending on the, the sign rule that you use. Let's put the negative sign. It's not going to make a difference here now, this negative sign having the negative sign or not, okay? So d2y by dx squared is negative m divided by ei, okay? Now, if this member deforms, let's try to find theta, okay? How much is theta, the angle here, theta, okay? So we know that theta is dy by dx, right? Theta is dy by dx. So that means that theta is the integration of this mei divided m divided by ei dx. Because negative m divided by ei is d2y by dx squared, so dy by dx is the integration. Okay? And how much is the moment at any point in a truss member? 0. So what's the integration of 0? No, not 0. Constant. Right? So what does this equation tell us? That theta is a constant value at any point, right? So what I'm drawing over here is a non-constant theta. Theta is changing. You have small theta here, here the angle of rotation is larger, right? That is not the case that we got. So what we got is when this member deform, it has to deform, it has to remain a straight line so that theta is constant, okay? There is no deformation in it, okay? So that's theta here. So what do we have here? That to have this theta, if this point is fixed or doesn't move, so actually this point just move a distance u, okay? So actually this theta is a function of u, right? Then theta is u divided by L, right? So if you know u, you can find theta. So theta is not an independent degree of freedom here. Okay? Your degree of freedom is U, not theta. Because theta is, you know, once you know U, you know theta, right? You understand this point? Tan theta is U divided by L. Once you know how much is U, how much is that displacement, okay, you know theta, okay? So theta is not an unknown or not an independent unknown, okay? So now this U, I can break it down into two parts, a displacement in the X, a displacement in the Y, okay? So those are the 2 degrees of freedom that we have. We don't have rotation here, okay? We don't have theta as a kinematic degree of freedom in trusses, because you don't, you know, theta is not an independent variable, okay? Once you know that those displacements ux and uy, you can find theta, okay? So the degrees of freedom, okay, for truss, there are no rotations, only displacements are allowed. So, if we're talking about displacements, how many displacements can happen here? Displacement in the X and displacement in the Y. So each node can have 2 degrees of freedom. What are those? A displacement in the X and a displacement in the Y. Those are the allowed degrees of freedom at each and every node. Those what can happen. So therefore, if we have those 2 degrees of freedom at each node, so how many degrees of freedom would we have in a member? 4. Each member has 2 nodes, starting node and an ending node, the near end and the far end. So therefore, for a member, 4 degrees of freedom are allowed. What are those? Ux at the near end, Uy at the far end, Uy at the near end, and then Ux at the far end, and Uy at the far end. So those are the 4 kinematic degrees of freedom that can happen in a truss member. Okay? 2 displacements at the near end, and 2 displacements at the far end, in the X and the Y. Okay? So that's the first difference. The kinematic degrees of freedom. In a beam member, you have theta and delta, right? At each node. Now, for the truss member, you have what? You have Ux and Uy, horizontal and the vertical displacement at each node. Okay? That's the difference. Okay? So that's the first difference here. Let's see. For the second step, calculating each member stiffness matrix. Okay? How does the truss element, truss member stiffness matrix look like? Would it look the same as the beam element? Definitely not. Why not? Because you have different degrees of freedom, right? The stiffness matrix relates what? Relates the displacements to the forces, right? That's K, relates the displacements to the forces. So now the displacements are different. I don't have a rotation, okay? So we need to go ahead and try to build the member stiffness matrix here, okay? So how we're going to do this? So we know the second difference here comes in the member stiffness matrix. We know that's going to be different. So how different it's going to be? We know P is KU. We want to find this U, okay? So let's say we have a member, a truss member that looks like this. It has a length L. And this is the near end, and this is the far end, okay? And this is the x-axis, and this is the y-axis, okay? This member is made of a material with a modulus of elasticity A and an E and an area of A, okay? So EA is the modulus of elasticity multiplied by the area. Okay? For a truss member, now this truss member that I just drew, it's horizontal. In a truss, any truss, your element or your members, you're definitely gonna have members that are not horizontal, right? You agree with this? For a beam, no. For the beam, they are all in the same direction. That's the definition of a beam, right? If you have a beam that has a member like this and then a member like this, then it's not a beam, it's a frame, okay? For a beam, it's just one member, or one, it's only in one direction. It can have more members, but they are all in the same, horizontal direction. That's a beam, okay? For a truss, definitely, a truss is a group of members, right? So definitely you're going to have vertical members, horizontal members, inclined members, okay? So this member that I drew right now is horizontal, okay? I can generalize this into any direction. We're going to do this later, okay? But now we're working in, this truss member. We're going to study the displacements along the direction of that member, in that x direction. So x is in the direction of the member, and y is in the direction perpendicular to the member, okay? So, for example, if I have a member like this, so where's x and y? X is in the direction of the member, y is perpendicular to the member, okay? So, now, how can we find K? We said K is what's the definition of the stiffness coefficient? K? It's the force due to a unit displacement, right? The force due to a unit displacement. So let's do this. Let's say we apply a unit displacement here. U in the direction of x, ux, at the far end. Okay? And let's see how much are those forces, okay? The forces that comes due to this displacement at the far end. You're going to have a force here. Actually, you have a member like this, you stretch it. So what you're going to have? Will you have a vertical force? No, you're just going to have a force in its direction. F, a force at the far end, okay, in the x direction, and the force at the near end. And you know that those forces are equal in magnitude and opposite in direction, right? How much are those forces? So what we did over here is we applied an axial displacement at F, at the far end of the member. UXF, okay? We want to find how much are those forces, UN and UF. What do we know? You know that this member, you just apply a normal or an axial displacement. You know the modulus of elasticity is the stress divided by the strain, right? The stress is the force, which is FF or Fn, okay, divided by the strain. This is the stress, sorry. The stress is the force divided by the area. And then the strain is what? What's the strain? What's the definition of the strain? Elongation divided by the initial length. How much is the elongation here? UXF divided by the initial length, which is L. So I have here E equal FL divided by UA. So that means that the force F is equal to EA divided by L multiplied by U. Right? So those forces, FF is EA divided by L multiplied by that U at the far end. And that force Fn is the same magnitude, but it's opposite in direction. So in the opposite in direction, so it's negative. What are those? This is exactly what we have here. P equal Ku. The force is equal to this multiplied by U. So this part represents what? K, the stiffness coefficient. Okay? So here, those gives me the stiffness coefficients. Okay? This is when you apply a unit or a displacement at the far end in the direction of the member. If you apply a displacement that is perpendicular to the direction of the member, you're not going to get anything. Okay? It's just a rotation in the member, okay? Because this is thrust member. It's a pin at the beginning, a pin at the end. So just having the vertical displacement here, it's not going to give you any forces. So we're not going to study the y direction, okay? We're not neglecting it, okay? But it's not going to give me any forces. The stiffness coefficients will be 0, okay? There will be no forces applying a force in that direction, okay? And then doing the same thing, but applying the unit displacement at the near end. So apply a displacement at n. So I have the same member here, that's n, that's f, and then I'm applying a unit displacement un, okay? So what I'm going to have here, I'm going to have two forces, F at the near end and F at the far end. Again, this is, an axial displacement, so I can apply the same rule that we just did, and we're going to find that Fn is EA divided by L multiplied by UN, and FF is the same force, but it's opposite in direction, so it's negative EA divided by L multiplied by UN. That again gives me the stiffness coefficients. Now, if I would like to rotate, if I would like to combine those coefficients together in a matrix form, okay? So combining So I want to write it in the form P equal Ku. I have a force at the near end, I have a force at the far end. Okay? Those forces are equal to K multiplied by the displacements. I can have a displacement un x and u far x. Okay? The other two displacements, u near UNY and UFY, okay, we said they're not going to give me any forces, so I'm not including them here, okay? Just combining those, okay, those values in red that we just had, okay? This is what we're going to have. As you see here, all of them you have EA divided by L, right? And then they are multiplied by UF, UN, UN, okay? So here I'm going to take EA divided by L as a common factor. And then here you're going to have 1, negative 1, negative 1, 1. What's this? I just combined those four values in a matrix form. Okay? So what does this stiffness matrix represent? What does this element represent? It's the force at the near end when you apply a unit displacement or a displacement UMX or a unit displacement at point n in the x direction. What does this number represent? It's the force at the near end when you apply a unit displacement at the far end. It's going to be negative EA divided by. Okay? So that's K. Okay? But this K, as you see here, those forces, this K, those displacements are in the direction of the member. Okay? we're going to name the direction of the member as the local coordinate system. So those are in the local direction. When I say the local direction, what does this mean? It means it's in the direction of the member. X is in the direction of the member. Y is perpendicular to the direction of the member. So those forces are in the direction of the member. Those displacements are in the direction of the member. Okay? So here, we're going to name this. This is the local load vector. Those are the forces in the direction of the member. And this is the stiffness matrix, but we're going to name it what? The local stiffness matrix. And this is the displacement vector, right? This is the displacement vector. But what type of displacement? It's the local displacement vector. Okay? Those displacements are in the direction of the member. So now, what if the member is inclined? So I have a member like this. That's the near end, that's the far end, okay? It's inclined with an angle theta, okay? And that's x. I'm going to use lowercase here, x and y. So x and y in lowercase represent the local coordinates or local axes of the member. Okay? But I have the global coordinates. Those are the x and y, okay? Generally, the global ones, okay? Not just for that member. I have an angle theta. This member is inclined with an angle theta. Theta is measured from the global x-axis to the local x-axis, okay? So here I'm using x and y in lowercase, okay? Are the local member axes, or the local member coordinate systems. And x and y in uppercase are the global coordinate system. What I want to do now, I want to write how can we write the stiffness equation in reference to the global coordinate system? Okay? So what I did so far here, I wrote P equal KU, but I wrote this in the local coordinate system, right? That was written in the local direction. P were the forces in the local direction. A here was the local stiffness matrix. Those displacements were the local displacements in the direction of the member. I want to write the same equation, P equal KU, but in the global direction. So P capital equals K capital U capital. How can I do this? So to write it in the global direction, U, the displacements here, should be in the global direction. P should be the forces in the global direction. And K is what relates those to each other. Okay? So starting with this, all I know now is this relationship. I want to transfer this from the local coordinate system to the global coordinate system. How can I do this? So let's see now. If I have that member, okay, this angle is theta, as we said. This is x, y, and this is x capital, and that is y capital. If I have, okay, a displacement here, if this node, the near end here, moves a distance like this, what's this? This is u capital. The local in the global direction, this is u x capital. At the near end, u n x, right? So I have u n x. If this node moves this distance here, how do I represent this in terms of the local direction? To move from this node n to this point here in the local direction, how can you do this? You're going to have two components. You're going to move like this and then perpendicular like this. This displacement in the direction of the member is u n x, but all lowercase. This is the displacement in the x direction of the local coordinate, right? And in the direction of the member. And then you're going to move perpendicular to the direction of the member, so that's u n y. U n y small, lowercase. So u n x is simply the addition of those two components, right? You can go from here to here or go like this and then like this, right? I just broke this displacement in the global direction into two components in the local direction, okay? So now, what's the relation between this global displacement, u and x, with those two local displacements? Do you know how much is there a relationship between them? Just have this, let's just have this, enlarged. This is u and x, this is u and y, and this is u and x uppercase. And this angle is theta. Exactly, it's just sine and cosine, okay? So what I have here is that u and x small, okay, is just u and x capital multiplied by cosine theta, and u and y is u and x capital multiplied by sine theta. Right? You agree with this? This is the relationship between the local displacement, those two local displacement, and this component of the global displacement. Okay? Here, theta is measured from the global x axis to the local x axis. So this is if we have u and x. What if I have the same member? This is the near end and the far end. And instead of having a u and x, okay, I had, this is, let's draw the coordinate systems here. This is the x, the y, and those are the global coordinates, x and y. and this angle here is theta. Let's say now we have a displacement of u and y. Point y moves globally the displacement u and y. How can I break this into two components? I'm going to have a component like this, and then a component like this. This is u and x, and this is u and y, small. The displacements in the local coordinate system. Okay? So in this case, we're going to have u and x is going to be u and y, that global displacement in the y direction, but it's going to be sine theta, and u and y is going to be u and y capital cosine theta. Okay? Because now this angle here is going to be theta. Okay? So now, the same decomposition that we did, okay, we can do this at the far end as well, okay? So the same kind of decomposition can be done at the far end of the member. So now let's say you have a un x capital, okay, in the global direction, un x, un y, uf x, uf y. Two displacements in the global coordinate at the near end and two displacements in the global direction at the far end. Okay? How much are the local displacements? I can have this in a matrix form. Okay? So u and x, okay, and u fx is equal to cosine theta, sine theta, 0, 0, 0, 0, cosine theta, sine theta, multiplied by those displacements, u and x, u and y, sorry, u and x capital, u and y, u f x, u f y. What's this? Where did I get this relationship, those numbers? If you have a u and x, the displacement in the x, in the global x at the near end, how much is u and x? It's just that displacement multiplied by cosine theta. That's what we had here. Right? If you have a displacement in the y direction at the near end, then u and x is that displacement multiplied by sine theta. Where did I get this from? From here. U and y sine theta. Okay? If I have a displacement in the x direction at the far end, in the global direction, how much is the displacement at the near end in the x direction, in the local direction? 0. It's a different point. They are not related. I have two nodes, okay? The near end and the far end. If this point moves, this point has nothing to do with it, right? It's a different node, okay? So there is no relation here. That's why you have zeros, right? And then for the far end, again, the far end displacement has nothing to do with the near end displacements. So you have zeros here, right? And similarly, as having cosine and sine here, you're going to have cosine and sine. Okay? So what do we have here? I'm relating, this equation relates the displacements in the local direction to the displacements in the global direction of a member. What about u and y? Okay, this is u and x. What about u and y and u f y? We didn't have those here. We only had u and x and u f x. U and y and u f y, we said they're not going to give me any forces, so I'm not interested in them. Okay? So now, this matrix equation, okay, relates what? Relates what I have here is the local displacements. I'm going to write it as u small. And what's this? It's the global displacements. Okay? I'm going to name this u uppercase. Okay? So what relates this u small to this u capital? This matrix is what relates them together. We're going to give this a name. This is the transformation matrix. So the transformation matrix transforms displacements from the local coordinate to the global coordinate and vice versa. Right? And we're going to name this T, the transformation matrix. So what do I have here? I have u small equals T u capital. This is 2 by 1. This is 4 by 1. So this is 2 by 4. Okay? Is it clear? Okay. Now, let's ask you a question. As we related now the displacements in the local coordinates system to the displacements in the global coordinate system through that equation, okay? Can we do the same for the forces? What would be the relation? So what is the relationship between local forces? What do I mean by local forces? Forces in the direction of the member, okay? And global forces. What do I mean by global forces? Forces in the global x direction and forces in the global y direction. That has nothing to do with the direction of the member. I can follow the same decomposition as we did here, but except that instead of being for the displacement, it's for the forces. So it's going to be the same relationship, okay? You're going to end up having the same relationship. If you don't believe me, just have a force in the global direction and resolve it into two components. In the local direction, you're just going to find that it's going to be, cosine and sine. Okay? So what I have here is that B lowercase is equal to T P uppercase. What do I mean here? That the forces, those are the forces in the local direction which is 2 by 1 is equal to the transformation vector. Sorry, the transformation matrix. The transformation matrix looks the same as we did before. It's going to be 2 by 4 multiplied by forces in the global direction. Which is 4 by 1. Okay? So let's write this in details so PNX, PFX, the forces in the direction of the member, is equal to the transformation matrix. How does this look like? Cosine theta, sine theta, 0, 0, 0, 0, cosine theta, sine theta, and then the forces in the global direction is P capital, okay? N X capital, P N Y, P F X, P F Y, forces in the global directions. Right? You agree with this? Okay. Now, what I want to do is what? We said we want to find that relationship, the relationship between the forces in the global direction with the displacement in the global direction. That's what I'm looking for. Okay? How can I find this relation? The only thing I know, and we proved that, is that I have this relationship. Okay? Let me write it like this. P equal KU, but I have this in the local coordinate system. Right? So how can I transfer this from the local to the global direction? So now, what is the relationship between the global displacements and the global forces? I would start from the equation that I know. P equals KU in the local direction. We proved this, right? So to transfer from B in the local direction to B to P in the global direction, what did we do? We had P equal T P capital, right? So I'm just going to remove this P small by T P global, okay? And K is the same. How can I transfer from U lowercase to U uppercase? What's that? T U uppercase, right? Okay? So now, if I just want to have P here, what should I do? I don't want to have this T, I want to move it to this side. I multiply by T inverse, right? Those are matrices. So P is T inverse K T U. Okay? And for those matrices, T inverse for the transformation matrix, okay? T inverse is equal to T transpose, the transpose of the matrix. Okay? The inverse of it is equal to its transpose. So P is T transpose K T U. What do I have here? P in the global direction is equal to this, multiplied by U in the global direction. Right? What relates P to U? It's the stiffness matrix. So my stiffness matrix is this. Okay? So that's P equals K U. That's the global forces equals to the global stiffness matrix multiplied by the global displacement. So K is T transpose K T. T transpose is what? Cosine sine 0, 0, 0, 0, cosine theta, sine theta, and then K was what? EA divided by L, multiplied by 1, negative 1, 1, negative 1, and then multiplied by T, if you do this multiplication, okay, what you're gonna end having, you're gonna have K as follows. You're gonna have EA divided by L, and then you're gonna have the following: C square CS CS S square, and then you repeat this again: C square CS CS S square, C square CS CS S square, C square CS CS S square. The only thing here that is different, those are negative, this part is negative, and this part is negative. What's C and what's S? Exactly. C is cosine theta, and S is sine theta. Okay, as you see here, it's 4 by 4. Why? Because it relates 4 degrees of freedom. Why do you have 4 degrees of freedom? 2 at each node. 1 in the X, 1 in the Y. The global X, the global Y. It relates those displacements, okay, the 4 degrees of freedom, to the 4 forces. Okay? In the global direction. Okay? So that's what we have here. Let me write this so that I make sure you understand what I say here. This is the angle theta, okay? From the global direction to the local direction of the member, I have here the near end, I have here the far end, I have 2 degrees of freedom here, U and Y capital, and U and X capital in the global direction, not the local direction. And I have here at the far end, I have UFY and UFX. For repetition, just let me write this here. The forces in the near end, in the Y and X direction, I'm talking about the global directions, and the forces at the far end in the global directions are equal to K, which is EA divided by L, C square, CS, CS, S square, negative, 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 okay, cancel. Multiplied by the displacements, which are U and X, U and Y, U, F, X, U, F, Y. That's what we have for a member. P equal K, U in the global direction. Okay? That's the difference that we had here. Okay? Again, what did we do now? Okay? We said if you have a truss, okay? We did all of this. The degrees of freedom are different. What are the different degrees of freedom? Instead of delta and theta for the beams at each node, now we have a ux and a uy, vertical and horizontal displacement at each node in the truss. Okay? We don't have theta. It's not an independent variable as we saw. And then calculating each member stiffness matrix, is it different? Yes. How does K look like for each member? It's so simple. It's that 4x4 matrix. It's not 6EI divided by L squared and 4EI divided by L. Or now it's what? It's just EA divided by L multiplied by this. This is the K for a truss member. This is the stiffness matrix for a truss member. That's the difference. And then you follow the same steps. Okay? Once you build each element stiffness matrix, okay, you can build the overall stiffness matrix by mapping the elements, and then you solve for the displacements and solve for the reactions. The difference, the only difference or the addition is finding the internal forces. If I ask you to find the internal force in the truss, we're going to see this in an example then. Okay? The last difference. So let's apply those steps. Let's see an example here on applying those steps. I have a truss that looks like this. It's 10 feet by 10 feet. This is node A, B, C, and D. And we have two diagonal members like this. By the way, this is an indeterminate truss because you have, two members, two diagonal members. So definitely this is an indeterminate truss. So you cannot solve it using what you learned in structural analysis 1. Okay? And then here you have a roller support in this direction, and you have a pin support at point B. On this truss, you have those forces applied. Here you have 4K vertical force and the horizontal force at point D that is equal to 2K. Thank you. So now, what are we required? What else is given here? EA. To solve this problem, you need to know EA, right? When to write the stiffness matrix of each member, it's function of E and A. Okay? So EA is constant. All the members have the same moment, the same area, the same modulus of elasticity, the same EA. Okay? Constant for all the members. This is what I mean by constant. It's the same for all the members. We're required here to find the reaction forces and the nodal displacement. How much does each node move? And the force in member BC. Okay? How much are the reactions? How much are the nodal displacements? How much does each node move? Okay, the displacement. And how much is the force in member BC? The way that we're going to find the force in member BC can be applied to find the force in any member. Okay? Not only BC. So now, we want to solve this problem. I want you to solve it. I don't want to solve it myself. I want you to solve it. What's the first step? The degree, the same steps as you did in the beam. Okay? So the first step is the degrees of freedom or the, notation. Okay? This is what we did in the beams, giving notations, right? So now, for giving notations, this is, going to be a little bit tricky, okay? More than the beams. Why? Because the members, okay, in the truss are not all in the same direction, so their direction is important, okay? So when we say the notation, I have to give notation to what? To members, to nodes, and to what? The degrees of freedom. Okay? How many members do we have here? 6. Yes. So I just have to label those. Just label them in any way that you like. So this member is member 1. This member is member 2. This member is member 3. And this member is member 4. And this member is member 5. And this member is member 6. Now, I want to label the nodes. How many nodes do we have here? How many nodes do we have? Is that difficult? 5 or 4? When you said 5, you said that this is a node, right?
That means we'd have more beams.
If you say that this is a node, that's not wrong, okay? But if you say this is a node, then this node breaks this member into 2, okay? So you're going to have actually, instead of having 2 members here, you're going to have 4 members here, okay? So just 4 nodes, okay? So that's node 1, that's node 2, that's node 3, that's node 4. You can label them whatever you want, okay? You don't have to stick to this labeling, okay? You can say 1, 2, 3, 4, whatever you want, okay? The labeling is not going to make any difference. Now, let me ask you a question. For member 1, where's the start and where's the end?
For member 1,
Yeah.
C to A.
Okay, in terms of the labeled nodes, 1 to 2, right? So if you say 1 is the start and 2 is the end, so that's the direction of the member. That's the local direction of the member. This is very important here, okay? We didn't have this in the beams. All the beam members are, in the same direction. Can you say that 2 is the start and 1 is the end? Yes, you can do that, but the direction is going to be the opposite. Why do I care about the direction? Because the stiffness matrix is a function of the direction of the member, right? The stiffness matrix has C and S, right? What's C and S? Cosine theta and sine theta. What's theta? Theta is the angle between the local direction and the global direction. So the direction of the member is very, very important here. Okay? Okay, what about member 2? Where's the start and where's the end? 1 to 3. Okay. 1 to 3, that's fine. Can you say it's 3 to 1? Yes, but the angle is going to be different. Instead of being 45, it's going to be negative 45. Okay? What about member 3? I chose here 1, 2, 4. For member 4, I chose here 4 to 3. Okay? For member 5, what I chose here is 4 to 2. Okay? It starts from 4, ends at 2. Okay? And for member 6, okay, I chose 2 to 6. Okay? So those are the directions of each member. Okay? So now let's go ahead. So now I labeled the members, I labeled the nodes. What else do you need to label? The degrees of freedom. How many degrees of freedom do I have? How many nodes do I have here? So for the members, I have 6 members. I have 4 nodes. How many degrees of freedom? 8. Why 8? Because you have 4 nodes, and each node can have 2 degrees of freedom. What are the allowed degrees of freedom at each node? Exactly. A vertical displacement or horizontal displacement. A vertical displacement or horizontal displacement. A vertical displacement or horizontal displacement. A vertical displacement and a horizontal displacement. Those are the 4 degrees of freedom that I can have. Sorry, the 8 degrees of freedom that I can have in this truss. Each node can move in the X and the Y. Okay? Now, you need to label those 8 degrees of freedom. What did we say about labeling them? You can label them whatever you want, but we said the easiest way is what? Labeling the unknown degrees of freedom first. Right? Exactly as we did in the beam. What are the unknown degrees of freedom? Let me ask you the opposite. What are the known degrees of freedom? Is there any degree of freedom that you know that displacement is equal to 0?
No, because you know where the force is.
When there is a support that prevents the motion, right? Is there a support here? No, so this node can move easily in the vertical horizontal direction. This one can move in the vertical horizontal direction. What about this node? Can it move in the vertical direction? No, why? Because the pin support is preventing it from moving in the vertical direction. Can it move in the horizontal direction? No. What about this node? Can it move in the horizontal direction? Can it move in the vertical direction? Yes. Okay? So the unknown degrees of freedom, the known degrees of freedom are those 2 degrees of freedom and this horizontal degree of freedom. Everything else, those two and this vertical one are unknown degrees of freedom. Okay? So I have 5 unknown degrees of freedom. Okay? And 3 known degrees of freedom. So I'm going to label them. I'm going to start with the unknown degrees of freedom. I'm going to give this 1, 2, and 3, and 4. And then 5 here is unknown as well. And then I'm going to label the known ones 6, 7, 8. Any labeling is good as long as you label the unknown degrees of freedom first. Okay? So I have 8 degrees of freedom. Okay? What are those? Vertical and horizontal displacement at each node. Those 8, I have 5 unknowns, which is the first, second, third, fourth, fifth. Those represents u, x at point C, u, y at point C. The third is u, x at point B, and u, y at point B. The fifth is u, y at point A. Those are unknown. And then the 6th, 7th, and 8th, those are known. Those are u, x, a, and u, x, what's that node B, and u, y, b. How much are those? Those are 0. Those are known. You know that those displacements are 0. Okay? Now, we're done with step 1. The notation, the kinematic degrees of freedom. What's the second step? What's the second step? each element stiffness matrix, right? So step 2, build each member stiffness matrix. How does the member stiffness matrix look like? I'm just going to write it here. K in the global direction. How does it look like? I'm going to give it to you on the test if you want, but it's so easy to remember. How large is it? 4 by 4. How does it look like? EA divided by L, C square, CS, CS, S square, and then it repeats again with negative sign here and negative sign here and positive sign. That's K. So what do you need to know to build each member stiffness matrix? What do you need? What do you have here? You need to know EA, it's constant for all the members. You need to know the length of each member, right? And you need to know this C and S. What's C and S? What's C? Cosine theta. What's S? Sine theta. So you need to know theta, the direction of each member. Okay? So let's do this. So here we're using the global direction. Okay? We're building this in the global direction. So let's do this. How many member stiffness matrix that we're going to build here? How many stiffness matrix we're going to build here? 6. We said we have 6 members. So I'm going to do this 6 times. Okay? For member 1, this is member 1. We said it starts from here to here. So where's the local x-axis? Where's the global x-axis? The same direction. So how much is theta from the local x, from the global x to the local x? 0. So for member 1, the length is 10 feet. Theta is 0 degrees. So how much is C? Cosine 0 is what?
1.
1. And how much is S? 0. Let's build this. Now I know C is 1, S is 0, L is 10. So K1 is EA divided by 10 feet multiplied by cosine square. 1 square is 1. CS is what? 0. 0. Sine square is 0. Cosine squared negative, cosine squared is negative 1. CS is going to be 0, 0, 0. And then negative 1, 0, 0, 0, 1, 0, 0, 0. You know what? That relates to the local stiffness matrix. You remember the local stiffness matrix? The local stiffness matrix was EA divided by L, 1, negative 1, negative 1, 1, those displacements, right? This is actually what I had here, but expanded. EA divided by L, 1, negative 1, negative 1, and 1, but I have zeros here. Why? Because those zeros represents the vertical direction. You remember we said in the vertical directions there are going to be zeros, right? There is no forces in the vertical direction. So that's why those are zeros. Okay? Now, let's do the same for all the members that I have. Okay? Fortunately, member 1 and member 4 has the same EA, the same length, the same theta, right? So this K1 that I build is the same for K1 and K4. and it is the same for K4 because they the same EA and L and theta. Okay? Let's do member 2, and then we're going to stop there. Member 2. So for member 2, I need to find L and EA and theta. For member 2, how much is the length of member 2? How much is the length of that member? 10 multiplied by square root 2, right? You have 10, so this one is square root 10 squared plus 10 squared, right? So 10 square root 2. How much is theta? Theta is from the global x to the global y. Sorry, from the global x to the local x. Where's the local x? This is the local x. So from here to here, how much is that angle? 45 degrees, positive 45 degrees. So for member 2, L is 10 square root 2, theta is 45 degrees, so how much is C? Cosine 45. If you're going to use your calculator, it's 0.707, but it's 1 divided by square root 2, and S is 1 divided by square root 2. Sine and cosine are equal here. Okay? So you go ahead and build K2, which is EA divided by the length, okay? And then I'm going to multiply the length, that 10 divided by square root 2, multiplied by those numbers, it's going to be 0.035, 0.035, negative 0.035, negative 0.035, 0.035, 0.035, negative 0.035, negative 0.035, and that repeats itself here, and that repeats itself here. I'm going to stop here, but there is something, if you remember, we have to label this. Those numbers relates what degree of freedom to what degree of freedom. We're going to do this next time. Any question? Okay.
Will the matrices be on our next test?
Yeah.
Both of them? Beams and trusses, or just beams?
Just beams.
Beams. And then the deflection of frames.
And then the deflection.
We did beams on the last test.
Oh, yeah, the slow deflection, the slow deflection of the face, yeah. By the way, before you leave, for the second midterm exam, okay, I guess we have it scheduled, I don't remember either.
I think it's the 15th. No.
Okay, so just,
Can we move it?
I'm not going to be here on the 13th and the 15th. So if you want to move it to the 15th, that's fine. You want to move it to the 15th or keep it on the 15th?
We're choosing between 13th and 15th?
Hmm?
We're choosing between 13th and 15th?
Yes.
Our test is what, on
Tuesday
the
and Thursday.
14th?